So welcome to week 3, chapter 3 in the textbook. You can see it's entitled Solar Radiation, one of the most important concepts actually in meteorology. So let's just click in here and start off here. Now solar radiation, this is radiation from the sun, is a form of electromagnetic radiation, right? And as you can see some of the definitions here. One of the important ones is going to be it's energy transmitted through space. That's what electromagnetic radiation is from the sun. And it does have both electric and magnetic properties, though for meteorology we're concerned mostly with the electric properties. All right. We'll take a look at a slide here in a second regarding wavelength. We'll show you what that is, the distance between successive wave crests or troughs, wave frequency, the number of wave crests that pass a given point per second. Important aspect down here is the speed of electromagnetic radiation being 186,000 miles per second, and we commonly call that the speed of light. And then here's just a diagram to show you the difference between frequency and low frequency and long wavelength, high frequency, short wavelength. The sun's radiation is definitely the shorter wavelength here. You can see that in the electromagnetic spectrum that the sun puts out visible light, but it also puts out infrared radiation, which is long wave, and it puts out very short wave radiation that is invisible to us, to the human eye, which is called ultraviolet radiation. All right, and you can see more details of that in the textbook. Let's go to the next slide here. The Wien's displacement law is what tells us what wavelength is going to be produced by an emitting body. So let me back up a little bit. Everything above absolute zero puts out electromagnetic radiation, but the frequency wavelength of that is totally based on the temperature, the surface temperature of that emitting body. And that's what the Wien's displacement law does. So you see you've got lambda max there equals a constant C over the temperature of the emitting body. So the only thing you really need to know here is that T being the temperature of the emitting body, the higher that temperature, you can see the smaller that number is going to be. That means the smaller the wavelength. So for example, when the sun puts the sun's surface temperature being about 6,000 degrees Celsius, T temperature is very small. That number is going to be very small. So that's one way we can demonstrate that the sun puts out very short wave solar radiation, and that becomes a very important concept in this course. So the sun puts out short wave solar radiation. All right. You can take a look at this graphic. It's also trying to demonstrate that relationship between temperature and wavelength. Just take a look at that in the textbook. And let's move on to this one here. All right, how does the sun produce its heat? Well, it's fusion. The sun is mostly hydrogen, and it fuses two hydrogens together to form helium. Now, when you fuse two hydrogens together, you give off an incredible amount of heat energy, and that's where the heat and the energy and the electromagnetic radiation comes from the sun. Now, as I mentioned here, the sun's surface is approximately 6,000 degrees Celsius, and as a result of that high heat, it's going to strip electrons off the helium and the hydrogen and send them off into space. We talked about that in chapter 2. This is what we call solar wind, and this is what these charged particles, when they enter Earth's atmosphere, only at the magnetic North Pole and the magnetic South Pole, those electrons and charged particles will interact with our atmosphere to produce auroras. All right, once shortwave solar radiation from the sun enters Earth's atmosphere from outer space, several things are going to happen to it, because it's going to interact with the gases in the atmosphere that are primarily oxygen and nitrogen, but some other gases, and it's going to interact with the aerosols. Remember what aerosols are. Aerosols are solid particles that are floating in the atmosphere, and depending where you are on Earth, they can be different things. Now here in the Southwest, Prescott, Arizona, our dominant aerosol in the atmosphere is dust. But if you go out into the coastal areas, it's going to be salt. And there are other things as well. Pollution adds a lot of aerosols to the atmosphere. So when solar radiation, shortwave solar radiation, enters our atmosphere, some of these gases will absorb shortwave, but not very well. Some of these aerosols are going to absorb or reflect some of this shortwave solar radiation. Cloud tops reflect shortwave solar radiation. So, when it's all said and done then, as you can see in my second little paragraph here, you can see that within the atmosphere, as it enters the atmosphere, we get some of the short wave is reflected. That's albedo. We'll talk about that later. Some of this short wave is transmitted, transmissivity. And if you want to really get a ballpark figure, about 50% of shortwave solar radiation reaches Earth's surface. So some of it is absorbed, not very much. A significant amount is reflected back, mostly by cloud tops, and about 50% then transmitted to Earth's surface. Okay, albedo. I mentioned that in the last slide. The term albedo means the reflectivity of a surface. So in other words, if you got a really light colored surface like a snowy surface, you're going to have a really high albedo, meaning a high percentage of shortwave solar radiation gets reflected back into outer space, okay? So the lighter the surface color, the higher the albedo. The darker the surface color, the lower the albedo, meaning the more shortwave solar radiation is absorbed by the surface, all right? You can read through here and see, and let's skip down toward the bottom. The global average oceanic albedo is 8%. That means 92% of shortwave solar radiation is absorbed by our oceans. They become a big, repository of the sun's energy. A lot of heat in our oceans. All right. Now here's a table. This is also in your textbook, just to give you an idea of some of the albedos of different types of surfaces. So you look down to fresh snow here. You look at fresh snow surface can have albedo as high as 95%. So over on table 3.2 here, you can see that you get about, it's indicating 47% of shortwave solar radiation is absorbed by Earth's surface. I like to round it off to 50 because that's just an average anyway. You can see that about 23% is absorbed by the atmosphere, and then you can see that about 30% is reflected out of the atmosphere. So this slide's taking a look at the ozone layer, and in the ozone layer resides in the bottom part of the stratosphere, just above the troposphere. And ozone is O3. Those are 3 oxygen molecules bonded together, and that has the capability to absorb most of the ultraviolet light that enters the top of our atmosphere. Ultraviolet light is deadly to most life forms on the planet, so this is a good thing. And until we had an ozone layer in place in our atmosphere, life really could not exist on land. So if you go back into the geological record, you'll see that land plants and land animals didn't start emerging from the ocean onto land until about 400 million years ago. And that was because it took that long for our ozone layer to develop and start absorbing and not allowing this ultraviolet light to reach our surface. All right. Now you might know, you might be aware, you may have heard of this, it's certainly in the book, take a look at it, that we started noticing an ozone hole, as it were, back around 1980-81. Now, we believe that the reason this ozone hole developed was that chlorofluorocarbons, we call them CFCs, and we use those in refrigerants and in producing styrofoam and things like that. We believe that the CFCs would work their way up into the atmosphere and just basically they would react with the O3 and break it down into O2 plus O. So in other words, they're breaking down the ozone layer. So in 1987, 197 signatories, countries, signed this thing called the Montreal Protocol that was going to reduce and ultimately ban the use of CFCs. That's the good news. The bad news is we really haven't seen a significant reduction in the ozone layer up until now. Now we think this is going to help, but we'll see. The future will tell what's going to happen with that. And you can kind of see it depicted here on a a graphic that it's mostly contained to the South Pole. All right. All right, long wave radiation. Now, I want to talk about long wave radiation here. When shortwave solar radiation passes through the atmosphere, like I say, approximately 50% reaches Earth's surface, and the Earth's surface heats up. But remember Wien's displacement law, right? The wavelength of the emitting radiation from a body is based on the temperature. Now, the temperature of the surface of Earth is much lower than the sun. As a matter of fact, about 15 degrees Celsius. So the surface of the Earth then is putting out long wave radiation, not short wave radiation, long wave radiation, because the surface of the Earth is much cooler. Long wave radiation goes up into the atmosphere. Our atmospheric gases, particularly our greenhouse gases, we call them, carbon dioxide, water vapor, and methane, are really good at absorbing long wave radiation. So essentially, our atmosphere heats up from the ground up. Our atmosphere is predominantly warmed by the ground, not by the sun, not by the shortwave solar radiation, but by the long wave radiation that is going outward and upward. And that's why it gets colder as we leave Earth's surface. All right. All right, taking a look at this again, staying with outgoing long wave radiation. Again, the textbook will talk about this in more detail. But there's a research scientist by the name of Stuart Callender, who, as you can see the dates, he was died in 1964. He was the first one that took a look at all of this carbon dioxide increase in the atmosphere and how this increase in carbon dioxide could effectively raise the temperature of Earth's atmosphere. And that's because carbon dioxide, which is a byproduct of burning fossil fuels, we know is a significant absorber of long wave radiation. So it made sense to him that if we were adding carbon dioxide to the atmosphere, that we would be increasing the absorption of long wave radiation from Earth's surface, therefore heating up the atmosphere. Now, I'm going to switch to this one right here. This is a record of the amount of carbon dioxide in the atmosphere from our research station on the summit of Mauna Loa on the Big Island of Hawaii. If you go back to 1960, you can see in that graphic the carbon dioxide in parts per million was around 315. Now today, I can tell you that this chart is actually a little old. It goes to 2010. In 2016, we have hit 400 parts per million. So that's a significant increase in carbon dioxide since 1960. So what we believe, this is what we believe, how humans are affecting climate change. We'll definitely talk more about this in the class. But if we switch to this one, we can see, if you go back to 1880, we can take a look at how temperatures were cooler then. And if we go on up to 2010, both on the ocean sea surface temperature from the middle graphic and the land graphic, our instrumental record, in other words a temperature record, is showing us quite clearly that temperatures are increasing. And there is definitely a correlation between the increase, go back to this slide here, you can see the increase in carbon dioxide, a greenhouse gas, and then you can see a concomitant increase in temperature. That's a correlation. Okay, what that means is that two things occur together. That doesn't necessarily prove that the increase in carbon dioxide is causing the increase in temperature, but there's a pretty strong probability that it is. Okay, I'll leave it at that for now, and we'll talk to you later.